Hello. In this lecture we shall talk about area bounded by a polar curve. Polar curves have equations r equals r of theta. Suppose we have one such equation where the graph is in the first quadrant, and consider the region where theta is moving between two values, theta 1 and theta 2, here on the picture, and the radius is moving between 0 and the curve. So you can see here the marked area, you can call it area under the curve. The formula for the area is given this way. It's 1/2 integral from theta 1 to theta 2 r squared theta d theta. How to derive this formula you can see in the book. Now we shall do some examples to compute areas. Let's start with something very simple. Sector of a circle. Let's take the circle r equals 3. Circle radius 3. And consider, for convenience, sector in the first quadrant. So this is the first quadrant. And let's take two values of the angle theta 1 and theta 2. And part of the circle between these two angles, like this. So this radius is 3. And the sector has this area. The formula will give 1/2 integral from theta 1 to theta 2. Radius is 3, so there will be 9 here, d theta. This is 9/2 theta between theta 1 and theta 2. So this is 9/2 difference theta 2 minus theta 1. If theta 1 is 0 and theta 2 is 2 pi, this is the entire circle. Area will be 9/2 times 2 pi, which will be 9 pi. Radius squared times pi. Familiar formula for the circle. Now, suppose we have a little bit more complicated area between two circles. So let's say again we have first quadrant for convenient picture. And we have again angle moving between theta 1 and theta 2. And I want to find area between two circles, one with radius 3 like before. So this distance is 3, and one with radius 1. Let's say this radius is 1. The area here is the marked between the two circles. So the region is described this way. Angle is moving between theta 1 and theta 2. Radius is moving between 1 and 3. This is our region. We can find the area by writing difference of two areas. The sector that we did before in the previous example minus the smaller sector with radius 1. So the area will be, I shall write the general formula first, theta 1, theta 2. 3 squared d theta minus 1/2 theta 1 theta 2 1 squared d theta. So the first area we already computed. This will be 9/2 theta 2 minus theta 1, and then minus 1/2 theta between theta 1 theta 2. So this will give 9/2 theta 2 minus theta 1 minus 1/2 theta 2 minus theta 1 will be 8/2, which is 4 times theta 2 minus theta 1. And if you have theta 1 to be 0 and theta 2 to be 2 pi, you have an entire ring to find the area. In general, if we have area between two graphs, let's do picture again, and between two angles, so that's theta 1 and here theta 2. Just a second. This angle is theta 2. And suppose we have one graph like that, another here. So the first graph is R1 theta. The first one, let's write it this way, R equals R1 theta. And here a smaller one, R equals R2 theta. And I'm talking about area between these two graphs when the angle is between theta 1 and theta 2. So this region is described this way. Theta is between theta 1 and theta 2. Radius is between R2 and R1. R1 is on top. And then we can write the area of this region as difference of two areas. 1/2 theta 1 to theta 2. Here the bigger graph, R1 squared theta d theta, minus 1/2 from theta 1 to theta 2, R2 squared theta d theta. We can unite in one semi-integral. That's not so important. The important thing is how to set up this integral, how to compute area between graphs. Okay, moving further. And let's do one graph now. This is the problem. Find the area bounded by the graph of the equation R equals 1 minus sine theta. So we have to graph this equation and figure out how to set up the integral. To graph it, here we do again a short table, assigning values to theta and r. The increment is power 2. Starting from 0, when theta is 0, sine is 0, radius is 1. Then going to power 2, sine is 1, 1 minus 1 is 0. Next step, pi, sine is 0, we have 1 again. Then 3 power 2, sine is negative 1, radius becomes 2. Then going to 2 pi, and 1 for the radius. So I shall sketch a picture here. When angle is 0, radius is 1. Let's say this is here 1. Then we're moving the angle towards power 2, radius is decreasing to 0. We'll get something like this. Then moving from power 2 to pi, radius is increasing to 1. On that side 1. Similar graph. Then we're moving from pi to 3 power 2. and radius is moving to value 2. Let's say 2 is here. So from this point we're connecting with this point here. And then from 3 pi over 2 to 2 pi, radius goes from 2 to 1. So it repeats actually this cardioid. Is the same symmetrical towards the vertical axis. Such a cardioid which you have seen before. When angle is moving between 0 and 2 pi, it's traced once in counterclock direction. So we are writing the area. This will be 1/2 from 0 to 2 pi, 1 minus sine theta of this squared d theta. Here we work the square. 0, 2 pi, 1 plus sine squared theta minus 2 times sine theta d theta. We can distribute the integral to each of these. So area will be 1/2 integral 0 to pi 1 d theta plus 1/2 0 to pi sine squared. To integrate sine squared, we had to use a formula mentioned several times. It's 1/2 1 minus cosine 2 theta. So this is to replace sine squared. Minus 2 times, we can reduce by 2, so it becomes just minus integral 0 to pi sine theta d theta. So we integrate. We have 1/2 theta between 0 and 2 pi. Then it becomes 1/4. And integrating 1, again we get theta 0 to pi. Then we integrate cosine 2 theta. This will give, it will be minus 1/4 sine 2 theta over 2. 1/2 in front, 1/2 from the formula, and another 1/2 from the integration. And this between 0 and 2 pi. And then we have plus cosine theta between 0 and 2 pi, integrating the sign, adjusting for the negative sign. Now computing the area, we have 1/2 2 pi, at 0 it's 0, plus 1/4 times 2 pi. Sine 2 theta at both endpoints is 0. Sine 0 is 0, sine 4 pi is 0. And from the last term also we get 0. Cosine 2 pi is 1, cosine 0 is 1. Subtracting, you get 0. So we have pi plus pi over 2, which means we get 3 pi over 2. This is the area of the cardioid. Okay, moving toward the next example. Again, find area of area bounded by the graph of r equals 3 times sine theta. That's a polar curve. Again, I'm writing a short table, assigning values to theta and the radius, starting from 0, 0 angle, 0 radius, then pi over 2, radius becomes 3. So it goes from 0 to 3. then pi, again 0, 3 pi over 2, negative 3, 2 pi 0. How does this look like? Here we have a picture. This is 0. When theta is 0, radius is 0, so starting from 0, 0. And then angle grows to pi over 2, radius grows to 3. Let's say this is 3 here. So we have such behavior. Radius is moving between 0 and pi over 2. Angle is moving between 0 and pi over 2. Radius goes from 0 to 3. Then we're moving the angle towards pi. The radius goes to 0 again. Something like that. Then moving from pi to 3 pi over 2. Radius becomes negative, it will repeat the same curve. For example, if you have this position here, you have to measure the radius on the opposite side, so you're getting points on the same circle. This is a circle. I think we already know that this is a circle from previous examples. So the curve will be repeated twice if you go from 0 to 2 pi. We don't want to trace it twice because then we get twice the area if you put such limit 0 to pi. We have to go from 0 to pi only this interval. So it's very important to understand how the curve is traced. It's traced once between 0 and pi. So we set up the interval for the area from 0 to pi. 3 times sine theta squared d theta. So this equals 1/2, 0 pi, 9 times sine squared theta d theta. 9/2, 0 pi. For the sine square again, remember it's 1/2, 1 minus cosine 2 theta d theta. So we have 9/4. Integrating 1 we get theta. Integrating the cosine we get sine, minus sine 2 theta over 2. All this between 0 and pi. Look, the sine at both endpoints will be 0. So we have 9/4 pi, theta between 0 and pi. This is our area. Good. Moving towards our next example. Again, find area, and we have this curve. Area surrounded by this curve. R squared equals 4 times cosine theta. Okay, how to plot this now? Again, starting with the short table. Theta r. Theta is 0. Then r squared is 4. R will be 2. Radius is 2. Moving from 0 to pi over 2, cosine becomes 0. So the radius will be 0. Then from pi over 2 to pi, the cosine becomes negative. All the way to 3 pi over 2 it's negative, so we have just to skip this interval. We don't have values for the radius here because it will be a complex number. Again, cosine becomes positive from 3 pi over 2 to 2 pi. So we continue from 3 pi over 2, where cosine is 0, radius is 0, and then next step 2 pi, radius is 2 again. So we have such an interesting situation. Here 0, starting at 2, moving angle towards pi over 2, we go with the radius to 0, like that. Then we're skipping interval from pi over 2 to 3 pi over 2. And then we go from 0 to 2. We just have a symmetrical part here. How to set up the integral? We can do this. We can use only the interval 0 pi over 2, compute the area of the upper part here, and then multiply by 2. These are two identical parts. So the area will be 2 times 1/2 0 pi over 2. R squared is given, 4 cosine theta d theta. So again, here it's very important to understand and to find correctly interval for theta. It should be 0 pi over 2, and then we multiply by 2. Okay, computing the area, we have 4 times sine theta between 0 and pi over 2, which gives 4, just 4. This is it. And here comes our last example. Again, I want to find area. It says one loop under the graph of this equation, r equals cosine 3 theta. So how to graph this curve? If we start with our table, what we get? Starting theta 0, radius 1. Then our regular increment is pi over 2, but look here, we will jump, when you take theta pi over 2, we'll jump directly to 3 pi over 2. So we have to follow important parts on the graph. Important parts are when cosine is 0, cosine is 1. And the next step after 0 will be when 3 theta is pi over 2. This will be theta equals pi over 6. When theta is pi over 6, cosine 3 times this will be pi over 2, cosine will be 0. So this is important step. And this is what corresponds to this interval. Starting at 1, we're moving angle from 0 to pi over 6. And let's say pi over 6 is like this. And radius is moving from 1 to 0, like that. Instead of drawing the entire curve by hand with smaller intervals with increment pi over 6, I can just show you the curve, the general shape, and you can see this on a calculator. It's very easy to graph. It looks like that. Very roughly, very roughly. 3 petals which are identical. One loop is 1 petal. What I have graphed using my very short table is half of a loop, only this part. And we can compute the area of this small part, and then multiplying by 2 we get the area of one loop. If you multiply again by 3, you get the entire surrounded area. So one loop area will be 2 times area of the marked region here. So this will be 1/2 from 0 to pi over 6. Cosine 3 theta squared d theta. So this will be 0 pi over 6 cosine squared 3 theta. Again, we have a formula. It's 1/2. Now 1 plus cosine double angle 6 theta, d theta. This is it. So this will be 1/2 integrating 1, that's theta. Integrating the cosine, we have sine 6 theta over 6. And we're going from 0 to pi over 6. This is now 1/2 times pi over 6. When you put pi over 6 in the place of theta, you get sine of pi, which is 0. And it's 0 on the other end. There is nothing else. That's all. That's all. So that's pi over 12. One loop. If you multiply by 3, all bounded area will be 3 times this. So this will be pi over 4. That's how we reason and that's how we work. All these curves we can graph on a calculator, but we have to be careful when we select the interval for integration. So we need to work with the small table and graph at least part of the curve by hand. We should not trace it twice. We can use all sorts of symmetry, like here multiply by 2, then multiply by 3. This is how we work with areas and polar graphs. Goodbye for now. The next lecture we shall talk about arc length with polar coordinates.